Byrne here talking about utilizing Ceph for large-scale, high-throughput storage to support the LHC experiments. Take it away.
Absolutely nailed it. Right, so hi everyone, I'm Tom, and I'm going to be talking about that, my experience of supporting the LHC experiments with Ceph. So, what is ECHO? So, ECHO is a large Ceph cluster that we run. It's based at the Rutherford-Apton Laboratory, which is a site in the UK that's a Science and Technologies Facilities Council lab. It's actually turned up in a couple of other talks today about stuff that I had no idea about, but I run the storage for, so that was cool. And yeah, its main users are the LHC experiments. So ECHO currently has 180 storage nodes, 5,000 OSDs, and we've got an extra 1,000 OSDs in racks, pretty much ready to go in when I get back, sort of. And yeah, it's all the data pools are EC 8+3. We use librados striper, so the Rados objects are all 64 megabytes, so they're fairly large compared to a lot of other clusters. And it's pretty busy. Most of the time we'll be seeing 20 gigabytes a second or more read rates to our analysis clusters. So yeah, and it's currently running Luminous, sort of testing, or beginning to start Mimic testing now. So you may recognize this diagram. This actually popped up in the talk at the beginning of the day. I want to try and provide a bit of context as to what we're actually doing, what ECHO is actually doing for the LHC experiments. And to do that, I need to explain a little bit about what the LHC experiments are doing with all this compute and storage. So, at RAU, we're a tier 1 site. So at CERN, there's a whole bunch of compute, and there's a whole bunch of storage for the LHC experiments. It's actually only about 20% of the total that's used by the LHC experiments. And the tier 1 sites provide around 40% of the compute and 40% of the storage. And the tier 2s provide the remainder. Having these large tier 1 sites with large amounts of storage allows CERN to keep a complete copy of the experimental data outside of CERN and allow the tier 1 sites to use their compute to do large-scale processing on the data, so you've got the storage close to the data. So at RAU, ECHO, the Ceph cluster, is providing all of the disk storage for the LHC experiments now at our site, and we've got a 800-node, 32,000 core batch farm, which is used for the processing. So what actually is this processing? There's a fairly large, these are big compute clusters, and there's 1 million job slots in the worldwide LHC computing grid. What is it actually doing? So, I'm not an LHC physicist. This is my experience of what they are doing from running the storage and talking to them. But yeah, so at the beginning, an experiment will collide particles together in a detector, and you get a raw output file, the unstructured data file. These are stored at the tier 0 and then are transferred to tier 1, so transferred into the tier 1 disk, so to ECHO in our case. As well as capturing data from real collisions, the experiments simulate large amounts of data from collisions that they're trying to investigate. So they have physics models that they're researching, and they produce simulated collisions from those. This data actually makes up the bulk of what is stored on disk, and stored on disk on the WLCG. And it's largely identical to the real data, and it's vital to actually get, it's like plays a really important step in the user analysis at the end of this. So yeah, once you've got your data, you then need to reconstruct it. You need to go from the detector readouts to the actual momenta and the trajectories of the particles in the detector. So this happens, again, usually at the tier 1s, or a large part of it happens at the tier 1s. And so the files are copied to the worker nodes, jobs run on them, the output files are then copied back to the storage, and this can sometimes happen in multiple steps, so you'll get intermediate output files that get copied to the storage. So yeah, so that's a little bit about what's actually happening. Let's have a look at some of the experiments we support and what that actually means, what sort of data rates we expect to see. So this is for the Atlas experiment. And this is every bin is a day on these diagrams. And so this is sort of the number of successful transfers and the throughput we see from one of the experiments we support. And so, yeah, the numbers are fairly large, and they're fairly consistently large. We can expect to see these day in, day out. Yeah. And then this is from CMS, which is another one of the experiments we support. You can see that this is a slightly different view, but that's the completed jobs that run on our batch farm, and so that's 200,000 completed production jobs in the past month, so the yellow one. And you can see that the production jobs, on average, have sort of 20 gigabytes or more input files and then produce a few gigabytes of output files. And all of those input files and output files are coming from the Ceph cluster we run, coming from Echo. So yeah, I want to get in more into how Echo is actually architected. But before I do that, I need to talk a little bit about the protocols we need to support. So again, this stuff was mentioned in the first talk of the day. So primarily, wide area network transfers are using grid FTP currently, transfers between storage endpoints. That is going to change, but that's what is in use currently. And jobs getting their input files and putting back their output files, that's done via X3D. So several years ago, CERN started working on these protocols. Started working on plugins for the protocols to work on top of Librados using Librados Striper. And we've carried on the development to get them working well for our use case. And it's probably worth pointing out that obviously we're using Librados Striper directly here. We don't have a file store. These protocols normally provide access to file stores, but we're just using their object storage functionality in this case. So yeah, so this is what the data access architecture of Echo currently looks like. So you've got your Ceph cluster, and we have a collection of currently 7 gateway machines in our gateway cluster, which can serve external sites. And initially, we started out, we only had those gateway machines, and so all our worker nodes were talking to our Ceph cluster via those gateway machines. We ran into some pretty heavy scaling issues once we started getting actual traffic, and so we decided we just containerized up our X-Route-D server infrastructure and now run it across all of our worker nodes. It actually works really well, and yeah, it's pretty cool. So yeah, the containers run on every worker node, and there's functional health checks that run. If the container is currently healthy, if the gateway is currently working when a job starts on it, there'll just be an entry thrown into the host file of the jobs container, which redirects all the traffic. If the gateway is currently unhealthy on that worker node, it won't get that, and the jobs will just use the external gateways as usual. It's a pretty clean solution and works fairly well. So yeah, this has really helped Echo. It's a lot happier now. The external transfers are much more stable now. They're not trying to contend with the internal traffic, and we have a significantly increased bandwidth capacity between our Ceph cluster and our worker nodes, which is really cool. It has obviously added a few challenges. Having effectively different infrastructures pretending to be the same endpoint can lead to some interesting issues when they start to differ, if you have configuration changes on one that doesn't affect the other. So there's been some interesting things there. And I think the main thing that's been really interesting is we now have over 800 gateways. Monitoring these has become, it's certainly a little bit more interesting. And so currently we're throwing all transfer summaries into Elasticsearch, which is, working pretty well, actually. Cool. So I want to get in, I guess, a little bit more into what it's been like monitoring a cluster of this size. And I should probably caveat all of this. We're saying Ceph has worked really well for us. We're running a 40 petabyte Ceph cluster with 5,000 OSDs, and for the most part, it has been behaving very, very well. And it's been behaving well enough to the point that we can effectively run it as a completely separate infrastructure and just administer it as a Ceph cluster and not worry about what's going on top of it, not have to worry about taking downtimes because things are going to affect client transfers. It just works, really. But having said that, at some point you're going to run into a problem. You're going to run into a performance issue inside of Ceph that is going to affect your external transfers. And then at that point, not having that monitoring is going to make life a little bit difficult. So, yeah, and so we currently didn't have that monitoring, or I felt we were missing that. And I think there's a couple of reasons for that. In part, it's due to we use Ceph directly, so we're not using any of the common things that people actually use with Ceph, which have some of them have some sort of like transfer monitoring built in. We don't get that, so we're kind of on our own in that respect. And the other thing is our users. Echo doesn't actually have users, really. The only things that interact with Echo are jobs running on a batch farm that have been scheduled by some central scheduling thing, or transfers between sites, which again have been scheduled somewhere else, and it's all automatic. If these things fail or have slow operations, slow transfers, it will either go unnoticed, or if it fails, it will probably get retried and then succeed. So for transient problems, this can make monitoring this sort of stuff, or it can make monitoring these transient problems quite hard. And what we began to see, or what we have seen recently, is as Echo has grown, as it's scaled, we have had the odd slow request. We have had issues that have started to crop up. And it's it hasn't been the easiest thing to really track how many of these we're having and specifically what they actually are. What pools these are affecting, why they're actually slow, and whether these are affecting our external transfers or our transfers to our worker nodes. It can, definitely feel like we're flying a little bit blind sometimes. So I threw together a few scripts to dump these slow requests. You can get really detailed information from the OSDs when they're either when they're experiencing the slow requests or get their historic slow requests. And then so I threw it into Elasticsearch and had a look at what was going on. So this was what I ended up with. This is definitely not it worked for me. So this is 12 hours of Echo, and so you can see the slow request histogram there, broken down by the experiment pools. And then that ridiculous-looking pie chart thing on the right-hand side is the breakdown of the pool, the placement group, the object, and then the request, the reason why it's stuck. So the main thing that's going on here is there's a large spike that happened, and that's affecting the Atlas pool. And so looking into this was this is a single Atlas object, and it's in fact an analysis table, which is used by a lot of different jobs that tend to be starting at the same time, and they're all stuck waiting for locks on this object. So this is something we occasionally see. It seems to be due to misbehaving gateways. So one gateway getting a lock on it and then not releasing it. I don't actually think this is a problem with Ceph itself, or I'm pretty convinced it's not a problem with Ceph itself, as most of the time files of this popularity are absolutely fine. And I think it's something that when you get a gateway crashing at the wrong time, you run into this problem. But being able to look at this transfer in our Xroot D monitoring and see, there was a big spike. The transfer rate absolutely plummeted for a while, but these are successful transfers, and so the jobs are coping with it, and the transfers are eventually succeeding. So this is something that I think is a problem in our gateway infrastructure rather than a problem in Ceph, which is nice to be able to make that, nice to be able to see that. So looking at files that aren't aren't related to that hot file, you can see that this isn't a single file anymore. These are they're not related to a single pool, and there's a whole bunch of different placement groups involved in this, and they're not. It's not like one event. There's a whole bunch of events through this time period. So yeah, looking at the event type distribution for this, it's mainly complaining about having to wait for a map. And this is actually due to something we're aware of with Echo currently. It's because of the size of the cluster and a couple of other reasons, it takes a very long time to create an OSDmap. So if an operation is in flight when a placement group needs to peer, it's then going to run into this and it's just going to have to wait for the map. This is something that's actually been fixed. We just need to wait. Well, I'm currently waiting for a release. But yeah, so this has been fixed, so it's no longer a problem. Or it will not be a problem in the future. And in the meantime, we can work on fixing it by reducing the amount of peering Echo sees. Being able to correlate this with the XRIC transfers, which we can see are failing when this happens, but we can also correlate it with the cluster state, and you can see OSDs crashing and restarting, usually due to unhealthy disks, and that's something we can fix in the meantime. That's something that us as the system administrators should be keeping a better eye on. So yeah. So after this was so much fun, I replicated the same thing for sort of randomly sampled OSD operations. It's basically what RBD top is doing, but at a OSD level and not specific to the Rados block device layer. And it's really, really useful to be able to look at what your cluster is actually doing, seeing, for instance, how long your OSDs or operations for a particular pool spend queuing in an OSD. Stuff like that is information that's quite